All right, welcome back to another video. I've got a really good one today. So I'm part of the AutoCon 4 Slack server, and this was posted in there recently, the Network Startup Resource Center. So let's take a look at the about. So this is it's a uh, website that provides educational content about technical internet concepts with a mix of video clips, reference documents, and command line examples. So this is a great resource. I think it comes out of the University of Oregon. It's this is a free and open resource, which is something I love on this channel. I'm not a fan of when education and advancement is locked up behind paywalls, especially ones that are unaffordable. I think anyone who is curious about something and wants to learn it should at least have the opportunity to learn the basics. Maybe when it comes to having to buy a home lab or something like that, then they're on their own. But this sort of stuff I'm really all about. So let's go ahead and do the BGP for all. I think that would be the best. We've also got so we'll start with the BGP. It looks like there's a campus network design and operations training as well. There's all kinds of training. I just think this site is wonderful, and I want it to be a part of my channel. So let's make that happen right now. And we're going to start with the BGP for all. We can also do the enterprise networking. We can also do perf sonar, end-to-end tool for monitoring and troubleshooting of multi-domain networks, network performance. It looks like a DMZ. So it looks like there's one, two, three, four, five different things you can learn about. Um, but we're going to start with BGP. All right, so Border Gateway Protocol is the primary routing protocol used to transfer data and information on the internet or autonomous systems. BGP is a path vector protocol which maintains paths to different hosts, networks, and gateway routers and determines the routing decision based on rules, filtering, weight, and community. Understanding the myriad options for routing can produce efficiencies for institutions and create opportunities for research and education networks to collaborate. So, got the whole thing mapped out here. We'll watch the intro video.
The internet is basically made up of internet service providers known as ISPs who connect to each other's networks. How does an ISP in Kenya talk to an ISP in Japan? How does that ISP talk to customers of the ISP in Japan and get responses back? How is this any different from communication between two devices on local Ethernet? Remember that two-way packet flow is needed for communication between any two devices. The ISP in Kenya could buy a direct connection to the ISP in Japan. However, this would not scale, for it would mean that thousands of ISPs would have to buy connections to all other ISPs they need to talk to, thereby making the operational costs astronomical. Instead, the ISP in Kenya tells his neighboring ISP what customers he has, and the neighboring ISPs pass this information on to their neighbors, and so on. This process repeats until the information reaches the ISP in Japan. This process is called routing. The mechanisms used are called routing protocols. Routing and routing protocols ensures that the internet can scale and thousands of ISPs can provide connectivity to each other, thereby creating the internet as we see it today. The ISP in Kenya does not actually tell his neighboring ISPs the names of the customers because the network equipment does not understand names. Instead, He has received an IP address block as a member of the Regional Internet Registry serving Kenya. His customers have received address space from this address block as part of their internet service, and he announces this address block on his router to his neighboring ISPs. This is called announcing a route. Routers use routing protocols to exchange routing information with each other. There are two types of routing protocols, namely Interior Gateway Protocol, known as IGP.
Oh, it looks like it's skipped on to the next video. I'm just gonna watch the watch it and then go through one by one. Okay, so here's the intro section. Okay, so it looks like it's all laid out. I guess what I was most interested in is I just wanted to test my existing knowledge. So we can see we've got some exercises here. So I just wanted to do all the exercises with my existing knowledge before watching the video. So how do ISPs interconnect with each other? Each ISP buys a direct link with other in the world. Each ISP connects to a few neighboring ISPs. There we go. Hopefully they're not all easy like that. The process by which ISPs uh, find out about other networks on the internet is called routing. When an ISP uses a routing protocol to inform a neighbor about its IP address block, it is called advertising a route, right? Let's see. Oh, no. Uh, oh, okay. When an ISP uses a routing protocol to inform a neighbor about its IP address block is called, it's not called advertising? It is in Juniper land, I think. Announcing? I think announcing is probably right. Okay, yeah, announcing. So I'll watch the video for that because I got that one wrong.
The internet is basically made up of internet service providers known as ISPs who connect to each other's networks. How does an ISP in Kenya talk to an ISP in Japan?
Oh, I already
How
watched
does
that one.
that ISP?
Um, well, I wish they had like a button to like skip through. I guess maybe there's a playlist button or something. Uh, don't see anything. So here's acceptable use. Um, okay, well, I'll finish that up. Okay, so I got 3 out of 3. So, uh, yeah, I wish this were updated a bit to because I found like the thing that I always find the most difficult when it comes to doing courses like this is like tracking your progress and where you left off and stuff like that. So I wish at the very least there was like a back and forward arrow so you could see where you came from and where you're going. You kind of can see that here a bit, but even here it's not like highlighted, right? So like I wish there was like a little star that showed up here or like down in ideally I think down in the section would be like forward would be here, back would be that, and then you just use the arrows down here to go through. But it's the content that matters. So, and I like how they have these quiz questions here. So let's keep going on these. So exercises. Which of the following are examples of a interior gateway protocol? Um, uh, Check all that apply. So just these two. Got it. An IGP is used between routers within the same autonomous network. True. I just want to see something as well because this is a little bit of a trick question, I think, because I think IBGP is an interior protocol. So if the answer is just BGP on its own without designation of whether it's used internally or externally, then yeah, I think the in the spirit of the learning and everything, yeah, this is an external routing protocol. But I think you can, let's see here. Do you think this is a little bit of a trick question where if it were listed eBGP and IBGP as two answers, so that you had five correct or five options to check rather than four, that the correct answer would be checking IBGP but not eBGP, and then checking OSPF and ISIS? Or do you think in that case you would have to leave IBGP and eBGP unchecked? Let's see. Oh, okay. Okay, yeah, it's not designed for intra AS routing. In fact, there's part of it's okay. Okay, I get it. Yeah, it's not designed for intra AS routing. In fact, when it's used that way, there's basically inherent flaws in its design that you have to get over. For example, by using route configuration or route reflection. So route confederation or route reflection. So yeah, okay, you would leave both of them unchecked. You can definitely, I think you can use IBGP as an IGP, but you basically wouldn't want to, right? Yeah. Yeah, the correct thing to do with IBGP is to redistribute the routes. Basically, you are going to use it intra AS, but you're just going to use it at the endpoints that contain eBGP, and then for actual heavy duty intra AS routing, you're going to redistribute the information into a real intra AS protocol, either OSPF or EIGRP or probably most likely ISIS if you're a service provider. Yeah. Oh, okay. Common trap redistribute. So what you're describing is conceptually right, but in production networks, especially service provider networks, the preferred pattern is slightly different from just redistribute everything. So the canonical design, canonical is a great word. It's the name of a company, the company that does Ubuntu, but just the basic definition of the word is included in a list of sacred books officially accepted as genuine. It's something that is um, the agreed upon, yeah, recognized rule, standard, or principle. Yeah, so it's like, yeah. So the best design, essentially, basically, what this word means. What actually works at scale. The roles are cleanly separated, so eBGP talks to other autonomous systems, learns external prefixes. IBGP distributes those external prefixes across the AS, handles policy attributes, traffic engineering. IGP. So yeah, so these wouldn't be, even if you made this distinction between eBGP and IBGP. The best answer to this question would be leaving IBGP unchecked. I agree with that. So the IGP provides the loopback and next hop reachability, carries only infrastructure routes, converges fast and predictably. This is the key mental model. The IGP carries routers, the BGP carries routes. Okay, that's interesting. The subtle correction, redistribution versus signaling. What you said, slightly risky phrasing. Redistribute the routes into a real intra AS protocol. Yeah, like OSPF or whatever. What actually happens in well-designed networks, IGP to BGP sometimes, um, loopbacks into BGP, but you almost never at scale redistribute BGP into your IGP. Really? Instead, IBGP redistributes prefixes. IGP carries only what BGP needs to solve next hops. Okay. Oh, okay. So that's why. Okay, I got you. Okay, I think that's an important distinction. Yeah, like you're gonna do you're not gonna do specific routes. You're gonna do general broad prefixes is what you actually redistribute. So I think that's an important um yeah, I think that's an important distinction to make that you're gonna redistribute very specific general broad routing statements into your IGP, prefixes rather than really specific routes. I think that's an important distinction to make. Do I have that right? Okay, so rule of thumb, memorize this. IGPs carry where routers are. BGP carries what destinations exist. Everything that violates that separation is done sparingly, deliberately, and with fear. Uh, what broad prefixes really needs, important nuance. You're correct that if you do redistribute into an IGP, it should be highly summarized, low cardinality. I'll get a refresher for what that word means. Number of set of elements. Okay, so you're not going to distribute a ton of stuff into it. Topology stable. Examples that are reasonable: a default route, a single aggregate. Yep, representing the external world. A summary loopback block. Examples that are not reasonable: customer routes, internet prefixes, anything that flaps due to policy or external conditions. So yes, broad general routing statements only. But here's the sharper correction. In most well-designed networks, you don't actually need to redistribute BGP to IGP at all. Even broad prefixes are often avoided. Instead, you let IBGP carry reachability, IGP carry loopbacks and links, default behavior handle the rest. When redistribution is used, um, okay, well, I man, okay, well, let's have it lab it up for me. Um, oh, yeah, let's have it lab. Okay, lab this up for me. So this is what we're gonna do. This is what we're gonna do. We're gonna take my lab here. We're gonna go to GNS3. And then we're going to say we're going to add a blank yeah, so we're going to enable agent mode, and we're going to say lab this up for me, please. Lab this up for me, please. Go to lab.grandposh.com, click GNS3, 3, make a new blank project, then drop and cable up the devices you need. When you are done, hit the play button at the top. Uh, then Then you can right click on each device to pull up a console on it and configure them. Boom. This is so cool. All right, so now it's creating a new project, and I'm totally sidetracked. Assistant lab project, he called it. Not a good name, but whatever. Let's do some more questions as it's working. Got that one right. So an EGP is used to convey routing information between autonomous systems. Of course, that's true. Oops, never checked the answer though. Let's make sure. Yep. Okay. What's the best way to scale your routing? Put as many routes as possible in your iGPQ. Oh, as few as possible in your eBGP. Use only static routes. Put as many routes as possible in your eGP and as few as possible in your iGP. So we just saw, based on our conversation with ChatGPT, what the answer might be. Let's check. Oh, wow. Okay. IGPs don't scale well to large numbers of routes. You should put just your own infrastructure routes in IGP and your customer routes and internet routes in eBGP. Okay. So let's give that over to the because my sense now who's right? Okay, they're right. The University of Oregon is right. The ChatGPT is still very unreliable, um, even in this day and age. It'll get better. It'll get better, but it might correct itself if I give it the screenshot and say, like, hey, I don't think you were right. I don't think what you were saying earlier was right. We'll wait for it to finish its work, though. Oh, what happened? It's blocked? No. Why is it blocked? Well, it'll figure it out. All right, so this one is obviously the right answer down here. Put as many routes as possible into your EGP, and as few as possible in your IGP. Got it. Your external gateway protocol versus your internal gateway protocol. All right, 5 out of 5. So move on to the next one. So see, there's no header, there's no orientation. Like that's what I need here is orientation. Like what section is this for, right? Like I think it's routing protocols, but I can't remember if it's internet routing or introduction to ISIS. So I need that somewhere to know. Otherwise, um, I'm just I can't orient myself, right? And if I click this, it just takes me to the first in the playlist. Oh no, okay. So this does help me orient
Routers
myself.
use routing protocols to exchange routing information with each other. There are two types of routing protocols, namely Interior Gateway Protocol, known as IG.
Okay, cool. So that does help you orient yourself. The video maps to here. So this should say internet. Yep, it says it right there. Okay, cool. So ISIS messages are sent in IP datagrams. False. They're sent in ISO datagrams. ISIS routers continuously send out linked state BPDUs. Yeah, they do. Oh no, they don't. I almost said the F word. ISIS routers send out hello messages frequently, but only send out LSPs when the network topology changes. Okay, so this is a good candidate. If I get more of these wrong, I will watch the video. Adjacency is when a relationship is formed between neighboring routers for the purpose of exchanging routing information. Yeah, sounds good to me. Okay. Which of the following problems could cause two devices to fail to establish a neighbor relationship? Check all that apply. So the link, obviously that. The link only works on one, obviously that. The hello. So now we're talking about ISIS. We're not talking about OSPF. So in OSPF, this would be true. In ISIS, I'm not sure. I think it's also true in ISIS, but if I get this wrong, then I've gotten two wrong, so we'll watch the video. Yeah, it's only true for OSPF, so I'll definitely watch this video. So only these two are correct, not this one. Okay. All right, so I got two of them wrong, so let's watch the video. We'll watch it on fast speed.
We're going to spend the next few minutes introducing the ISIS routing protocol. ISIS stands for Intermediate System to Intermediate System, and it's the OSI routing protocol for CLNS traffic, specified originally in ISO 10589 document.
Yeah, and notice how it's for CLNS traffic. It's not for IP traffic, but you can but it has added IP support.
It's a link state protocol with two-level hierarchical architecture, and it has type length value options to enhance the protocol. Of most interest to us in the internet today is RFC 1195, which added IP support to ISIS, and it's known as integrated ISIS, although we just talked about ISIS. The notable thing about ISIS is that it runs on top of a data link layer, unlike IP-based protocols which run on IP. ISIS is known as a link state routing protocol, and the other well-known one, which we will also cover, is OSPF. Each node in the network computes the map of connectivity through the network. Both ISIS and OSPF use Edgar-Dijkstra's algorithm for producing shortest path tree through a graph, and you can read more about Dijkstra's algorithm in the reference shown. The other type of routing protocol is distance vector, and the common distance vector protocols are EIGRP, which is exclusive to Cisco, and RIP, where each node shares its view of the routing table with other nodes in the network. Routers with ISIS enabled on them look for neighboring routers also running ISIS. Hello protocol data units, or PDUs, are exchanged. The hello packet includes a list of known neighbors and details such as the hello interval and the router dead interval. The hello interval is how often the router will send hellos. Hello intervals are usually of the order of a few seconds, 5, 10, 15, depending on the vendor defaults. The router dead interval is how long to wait before deciding the neighboring router has disappeared. The router dead interval is usually a multiple of the hello interval, so maybe 3 times hello intervals, or in other words, 3 hellos have been missed, and that allows ISIs to determine if the neighbor has disappeared. The values of hello interval and router dead interval do not need to match on both neighbors, unlike in the case for OSPF. When a neighboring router responds with matching details, a neighbor relationship is formed. A relationship is formed between neighboring routers for the purpose of exchanging routing information, and this is what we call an adjacency. Once an adjacency is formed, neighbors will share the link state information. Information goes in a link state PDU, or more commonly called LSP. LSPs are flooded to all neighbors. New information received from neighbors is used to compute a new view of the network. When a link fails, new LSPs are flooded, and the routers recompute the routing table. ISIS operating across the network, all routers across the network form neighbor relationships with the directly attached neighbors. Each router computes the routing table. Once each router has the same view of the network has converged. The IGP design for a network is crucially important to ensure scalability and rapid convergence. The general rule, the fewer the prefixes, the faster the convergence. Network operators pay close attention to the IGP design to minimize the number of prefixes so they get the fastest possible convergence of the IGP.
All right, so this is good. Okay, so this was the introduction to ISIS. All of that went over my head, so let's just move on to the other one. So ISIS can carry IP, IPv6, and CLNS routes. That is absolutely true. That's why it's awesome. OSPF3, you can't do any IPv6, and certainly can't do any CLNS. I don't even know what that is. Um, all networks need to have level 1 and level 2 ISIS routers. I think that's false. I think you only need to have, yeah, so small to medium networks need only level 2, which is the backbone area, which is confusing. You would think it would be level 1. Okay, so drag the words into the correct boxes. Blank networks, so this would be probably multi-axis networks. Select a blank LS, so just This would be designated IS, intermediate system, which is responsible for sending the um, MAC address to other routers on the same uh, segment. The router with the highest configured priority wins the election. Oh, no, this must be MAC address. Oh, no, this must be priority. If this is not set, then the router with the highest MAC address wins. Okay. I think this is LSP link. Yeah, so let's check. Perfect, got it right. So multi-access networks elect a designated intermediate system, which is responsible for sending the LSPs, which in this, see, part of the reason why networking is so difficult is because we have all these acronyms, and the acronyms are the same but mean different things in different contexts. So in the context of MPLS, this stands for label switched protocol, or label switch packet, or something. I don't even know what, if that's right, but it stands for something else here in ISIS, and that's what makes it so hard to learn networking a lot of the times. Not only do you have to learn all these really bizarre acronyms that like don't map well to what they actually mean, um, the context differs, and the same acronyms are used, and you just have to know what does LSP mean from one context to the next.
ISIS has a two-layer hierarchy. We have level 2, which is the backbone, and we have level 1, which is the edge. A router can exist as a level 1 router, or a level 2 router, or as a level 1-2 router, where it sits in both level 1 and level 2. Most networks today can quite happily use just level 2. ISIS is multi-protocol. Integrated ISIS carries CLNS and IPv4 address families. RFC 5308 adds IPv6 address family support, and RFC 5120 adds multi-topology support. ISIS, of course, is extended to carry IPv6 prefixes through RFC 5308. And it can share topology with v4, where the v4 and v6 topologies are identical, or we can use multi-topology, which means that IPv6 topology is independent of IPv4. The latter is preferred as it allows network operators to incrementally roll out IPv6 completely independent of IPv4. There are two types of links in ISIS. There's a point-to-point link, where only one other router is on the link, forming a point-to-point adjacency. And there's a multi-access network, for example, Ethernet, where there's the potential for many other routers to be on the network with several other adjacencies. ISIS in multi-access networks has optimizations to aid scaling. One router is elected to originate the LSPs for the whole multi-access network, and this is called a designated intermediate system, or DIS. Other routers on the multi-access network form adjacencies with the DIS. There is one designated router per multi-access network. It generates the network link advertisements and assists in the database synchronization, and this lets us scale ISIS for multi-access and Ethernet networks. To select the designated router, it is configured by priority, and it's done per interface. Most network operators manually configure their chosen DIS with the highest possible priority. Typically, there will be two high priority routers on the network. Even though ISIS only chooses one to be the DIS, operators would select one router to be the highest priority, 127, and a backup router to be the next highest priority, 126. In the absence of any priority set, the routers on the multi-access network will determine priority by the highest MAC address. And the best practice is really to try and avoid this. If an Ethernet card on the multi-access network changes, the device gets a new MAC address, and it's quite likely there'll be a different DIS. To avoid this lack of determinism, operators will manually configure the priority, so the DIS is always the same device.
All right, cool. So this was the introduction to ISIS levels. Okay, so that was this one. So now adjacencies. All right, so we'll check in on our lab. Okay, everything's up. Everything's up. Let's see what it says about being wrong earlier, if it acknowledges that or anything. Okay, so there we go. So let's take a look at what the lab looks like that it made. Okay, so it just made one device. That's it. Um, please answer yes or no. We'll answer no. I already answered yes though. Uh-oh. Oh, what kind of device? So it dropped a Cisco. What does it say about what it did? So created a black. I just ready for me to configure. Ready for me to configure? No, no. Okay. Oh, it is? Okay. All right. Well, what do you mean ready for me to configure? I want you to configure it. All right. So go back to you doing the exercises. On Cisco iOS, a command like router ISIS XXX enables the routing process. The process ID XSS must be um, the same because no, it's the same because it's like a area ID. No, God, I'm so close to just, it has to wait, what? Oh, it's none of the above because it's a yeah, the process ID is not sent over the network, so it doesn't matter what value you use. Okay. Well, then it can be different. Oh, it doesn't have to be the same or different. But the network entity title NSAP must be different on every router. Okay. In iOS, you can use the commands show CLNS neighbor and show ISIS neighbor to check the state of your adjacencies. And that seems true. Yeah, true. The NSAP address was constructed from what loopback address? Okay, yeah. So ISIS starts with 49. So I think I think yeah, it's sandwiched. So it's gonna be ending in 40. Oh, right, and then there's weird syntax. I think it was this one. Let's see. Yeah, so pad each number to three decimal places and then regroup as three sets of four digits. The leading, yep, and the trailing are fixed. Yeah, I remember that. So yeah, you pad it out. And how does the padding work again? It's been a while since I went over this. Um, okay, so you pad it out to. Oh, okay. So it works by padding out each octet with a leading zero, dropping the dot, and then regrouping into groups of four. So let's go over that in Notepad. We're just going to take a random. I'm just going to do a random address. So we'll do 11.53.178.3. Okay, so now we have to pad them all out to be three digits. So we do that with leading zeros. We don't have to do it on 178 because it already has three digits, and we have to do it twice with uh, the last one because there's only one digit. So now we drop all of the dots, and now we add the dots back in every four rather than every three. So now we add the postfix, which is just the same for every ISIS, and then we add the prefix, which is the same for every ISIS as well. And I think is it 0, 0, 0, 1? Yeah, it is. Okay, so I had it right at the beginning. And now we have now we have the uh, NSAP address. Um, there we go. That's how that works. Because it's so easy and it's so easy and intuitive. It's like it's like counting to, it's like learning your ABCs. Just simply pad it out with leading zeros, drop the dot, add it every four digits, and then add the prefix and the postfix. Easy as one, two, three. All right. Okay. So, which of the following are ISIS best practices? Check all that apply. All right, I might have to watch this video because I don't know. So check all that applies. So leaving the metric interface At its default, I think so. Using passive interface, if you want to distribute the interface's subnet through ISIS, but not send in hello, but it's just, that's always a good one. Should do that in OSPF as well. Configuring the ISIS process to run as level 1 only, definitely not. Enabling wide metrics, oh, definitely. Um, Configuring each interface metric according to your metric design. I mean, I feel like it's this one. Let's go with that one instead of that one. There we go. Got it right. Perfect. Okay. Did better on that than I thought I would. All right. So which interface does a ISIS does ISIS choose to send out a packet to a given destination address? The interface with the lowest metric, the interface where the sum of all ISIS metrics across the entire path to the destination is lowest. Now remember, it's a link state protocol, so it's so I think this one's right. The interface which is carrying the least amount of traffic, the interface with the highest available bandwidth. So let's see. Yep, I got it right. The shortest path first algorithm is used in ISIS as well as OSPF. So it finds the path with the lowest sum of costs to the destination. What happens if two possible paths have the same total end-to-end cost? So the router load balances traffic between links. The router picks the interface with the highest MAC. Definitely not C. This is a configuration error that should not happen. The router picks an arbitrary link. I think it goes with the highest MAC. Let's see. Nope. Then I think it load balances. Yep, it load balances. So this is probably worth watching. There you go. Let's watch it because I got that one wrong.
Looking at some of the best configuration practice for Cisco iOS. Cisco's default is for all routers to be L1, L2. And this is suboptimal because all we need is for routers to be an L2 only. Once ISIS is started, other configuration is also required for Cisco iOS. Log adjacency changes captures adjacency changes in the system log and of course can be exported to a log collector for further monitoring. There are two types of metrics supported in iOS. We need metrics to be wide, which gives us a 24-bit range. The default metric in ISIS, as in iOS, is only 6 bits, which is not much scope at all for networks today. We set IS type to be level 2 only. This is a router-wide configuration. And then finally, we set NET address, as I described earlier. To activate ISIS on an interface, we go to the actual physical interface and add in the command line IP router ISIS and the process ID. This will tell ISIS to look for neighbors on that interface to form adjacencies with. And it also puts the interface subnet address into the link state database. If we don't want to have ISIS running on interface, we go to the actual process command and mark that interface as passive. That will still put the IP subnet used on the interface into ISIS, but will not look for any adjacencies. If there's no ISIS configuration for any interface at all, then CLNS will not be run on that interface and no subnet will go into link state database. All interfaces in ISIS have a default metric of 10. This is fine for a uniform backbone with equal size links, but most backbones have different link capacities between the routers and the POPs. And today, many operators will set the default metric to be a very large number, for example, 100,000. And following that, many operators develop their own interface metric strategy. The higher the bandwidth, the lower the metric. And you can set in Cisco iOS the metric simply by going to the interface and using the ISIS metric command. Care needs to be needed as the sum of the metrics determines the best path through the network. ISIS will choose the lowest cost path from end to end, and it will load balance across paths with equal total cost to the same destination. In the example here, the best path, lowest cost, is 11. If we go from the user to the content the user is observing, one path has a total cost of 15, the other path has a total cost of 11. In the second example, both paths have a cost of 15. So ISIS will load balance over the two paths, even though from the user perspective, one path starts off with 2 megabits uplink and the other one with 10 megabits. Operators need to be very careful when calculating the costs across the network, as there could be unintentional load balancing happening in parts of the infrastructure.
Well, that was the only thing I was able to see in this entire video was that the guy has a tongue ring as if he were a 13-year-old girl. But the yeah, okay. Anyway, let's move on to the next one here. So introduction to ISIS configuration on uh, Cisco iOS. Let's see here. I guess that would be more of a ear piercing. Not. I think that's a bit young for a Okay, this guy's where it's at. This guy knows what's up. So let's see here. Next is authentication. Okay. Yeah, I guess if you were a 13-year-old girl, it would be more like a ear piercing than that's a bit young for a tongue piercing. All right, let's see here. So why is it recommended that you enable ISIS neighbor authentication to secure the user traffic on the link, to establish adjacencies more quickly, to prevent bringing up adjacencies to a rogue router? None of the above. Um, authentication. Um, yeah, to prevent it to a rogue router. Got it. To make ISAS more efficient on a point-to-point link, you could enable neighbor authentication, disable DI. Oh, yeah, it would be this one. Disable DIS election, originate default route, reduce the router dead interval. Let's see. Yep, that's right. Fill in the missing words. There can be a maximum of blank keys in an ISIS keychain. This one I don't know. Let's go with three. All right, let's go with one. That one would have been my original answer. No, okay. Let's go with five. Nope, we'll try 10 next. All right, let's just watch the video and then get it from there.
Neighbor authentication is highly recommended. It prevents unauthorized routers from forming neighbor relationships and potentially compromising the network. Now, you might argue that ISI's usage is very limited across the internet, but it still doesn't prevent an enterprising third party from trying to compromise the infrastructure. The way to do it in Cisco iOS is to create a suitable keychain containing the key that's going to be used for the neighbor authentication. And then that keychain is applied either per interface, which is less common, or applied to the entire ISIS process, which is more common. You really want the key to ensure that nobody accidentally tries to add a router to the network infrastructure. But some operators will apply the key on a per interface basis. To originate a default route into ISIS using Cisco iOS, there's a default originate command, which will always originate a default route into ISIS, even if there's no default in the RIB. If we want to originate a default route conditionally, in other words, only if a default exists in the global RIB, then, as the example shows, we need to do the default originate command with a route map that will actually match a default route that will be seen in the RIB. The example is for v4. There's an equivalent that can be set up for IPv6 as well. Running ISIS on a point-to-point Ethernet also gives access to an optimization. We don't need a this on a point-to-point link. So what we can do is set up the Ethernet as a point-to-point link. Ethernet is widely used now for medium and long-haul point-to-point links, so we can save a little bit of resource by not having a DIS there. There's no need for one on a point-to-point link. And that's done by going to the Ethernet interface and doing ISIS network point-to-point. Both ends of the link need to have this configuration set up. As the DIS selection is independent of IP, the above command is generic. There is no need for an IPv6 equivalent. To add v6 support in ISIS, all we need to do is go to the interface and do IPv6 route ISIS. There's no other configuration needed if we're running it in a single topology-based network. For multi-topology, we need one more configuration line, and that's going into the ISIS subconfiguration for v6 and adding multi-topology. This will cause the router to create a separate topology database holding all the v6 destinations. To summarize all this, ISIS is a link state routing protocol. It's quick and simple to get started, but it has a myriad of options and features to cover almost all types of network topology. Network operators keep the ISIS design very simple. Most networks today can run the entire backbone in L2 only. And it's very much become the chosen IGP when operators are using both IPv4 and IPv6 in a dual stack configuration.
Yeah, ISIS is underrated. All right, so 255. Okay, so default information originate will always originate a default route into ISIS even if no default route is in the RIB. Oh, true. All right, so this was ISIS authentication, default routes. There we go. So next, oh, now we're going into OSPF, the one that's not as good because you have to set up V2 and V3 if you want to do IPv6. Or, well, if you are only doing IPv6, if you want to do both IPv4 and IPv6, ISIS can handle both, and you don't get as sophisticated traffic engineering metrics to play with. OSPF sucks. So OSPF is a bad routing protocol that's worse than ISIS. It's not there. It can only handle like 30 routers in the backbone too, right? I hate OSPF. Let's tell the hey, I kind of hate OSPF. It can only handle like 30 routers in the backbone, right? Like it's I like ISIS better, and then with ISIS you can do more sophisticated traffic engineering because you've got more granularity in the metrics. And not only that, you don't need a separate instance of it to run IPv6. It just encapsulates it as data. ISIS is awesome. OSPF is terrible. ISIS is awesome. OSPF is terrible. Let's see what it has to say about that. Okay, so it created the console. Okay, blah blah blah. Blah. Next step would be figures. Whereas red and telnet consoles were blank or blocked in the available at the moment. Okay, well, I don't know why that's the case. Uh, reload. Already started, so I'm going to stop them all. Oh, let's see here. Subject heard misconceptions, scalability. Hmm. Put them in different areas. It's not terrible. Okay, so OSPF is a link state protocol like ICS, true. OSPF tests whether a link is up or down by um, sending and receiving hello packets, of course. An OSPF router sends link state advertisements to all its neighbors. True. Oh, right. Oh, right. No. The router only sends LSAs to those neighbors with which it has formed an adjacency. Well, that's kind of pedantic, but it's the better answer. When a link changes state, new LSAs are flooded through the network and convergence takes place. True. All right. Which one did I get wrong? I got one wrong. Let's watch it. It's my punishment. It's in
So in
Spanish.
this section, we're going to take a look at OSPF. OSPF is the Open Shortest Path First routing protocol. Open means it's an open standard. It doesn't mean opening as in opening and shutting.
Sounds
An open
Irish.
especially means an open standard, developed by the IETF, by the OSPF Working Group for IP networks, and first documented in RFC 1247. The current version of the standard is OSPF version 2, documented in RFC 2328. The shortest path first in the name refers to Edgar Dijkstra's algorithm for producing the shortest path tree through a graph, and you can read all about that in the reference below the paper that Dijkstra produced in 1959. OSPF is known as a link state routing protocol. The other link state routing protocol is ISIS, where each node in the network computes the map of connectivity through the network. The other type of routing protocol is known as distance vector. Examples of distance vector protocols include Cisco's EIGRP and RIP. Each node here shares its view of the routing table with other nodes. Routers with OSPF enabled on them look for neighboring routers also running OSPF. To do this, they use what's known as the hello protocol. The hello packet includes the subnet mask, list of known neighbors, and details such as the hello interval and the router dead interval. The hello interval is how often the router will send hellos, and the router dead interval is how long to wait before deciding a router has disappeared. The values of hello interval, router dead interval, and subnet mask must match on both neighbors before an adjacency is established. When a neighboring router responds with matching details, a neighbor relationship is formed. A relationship is formed between selected neighboring routers for the purpose of exchanging routing information, and this is what we call an adjacency. Not every pair of neighboring routers become adjacent. On multi-access networks, for example Ethernet, only selected routers will form adjacencies. Once the adjacency is formed, neighbors share the link state information. Information goes into a link state packet, or LSP. LSPs are sent to a neighbor, and these are known as link state announcements, or LSAs. New information received from neighbors is used to compute a new view of the network. New LSPs are flooded, and the routers recompute the routing table. All routers across the network will form neighbor relationships with their directly attached neighbors. Each router computes the routing table. Once each router has the same view of the network has converged. The IDP design for a network is crucially important to ensure scalability and rapid convergence. The general rule, the fewer the prefixes, the faster the convergence. And network operators work really hard to make sure they minimize the number of prefixes carried in OSPF to ensure the fastest possible convergence of the protocol.
All right, sounds good. So that was the which one was this? So this is Introduction to OSPF. Okay, so next is areas. An OSPF only needs one single area. Um, and this is a strange question because like there's an argument for both. So in order for it to run, that's true. But as it grows, it very quickly does need more than one. Let's try true. Okay, yeah, only area 0 is required. This will work well for networks up to 300. Oh, I thought it was like 50. I mean, the convergence, yeah, I guess I'm skeptical that it can go up that high. But I guess it depends on what you're using. To deploy OSPF on a dual stack, IPv4/IPv6 network, you will need to, yeah, you need to run both, which is why it's terrible. You must manually configure a unique router ID on every OSPF speaking router. I think that's true. Oh, no, no, it's not. Okay, so the punishment is I watched the video. You don't have to do this. If you don't, one of the router's interface IPv4 addresses will be used as the router ID. Drag the words into the correct boxes. In a blank network, so a multi-access network, a designated router and backup router are elected. The winner is so this is not a point-to-point network, but you have to configure it as such. The winner is the router with the highest blank configured, so that would be uh, priority. If this is the same, then it goes to the highest uh, router ID. The router ID, if not set, defaults to the router's loopback address. Or if it does not have one, the highest interface IPv4 address. There we go. All right, so introduction to OSPF areas. So next is adjacencies. On a multi-access network, the designated router and backup designated router form adjacencies with check all that apply. All other OSPF speaking routers across the entire network. Uh, oh, the designated router and backup router form adjacencies. Uh, this is interesting. Um, this is a good question. On a multi-access network, the designated router and backup router form adjacencies with check with all other OSPF speaking routers across the entire network. I don't think that's true. I think C is probably correct. Okay, yep, I got it right. All right, and OSA in iOS, so Cisco, neighbors which are not adjacent are shown as which are not adjacent. Um, uh, which are not adjacent. Admit? No. Gotta watch the video. My punishment. So two-way is the right answer. All right, punishment.
On multi-access networks, the designated router and backup designated router form what are called full adjacencies. They form those with each other, and they form those with all routers on the multi-access network. Databases are synchronized, and the LSAs propagate along the adjacencies as the diagram shows. Otherwise, neighbor relationships between routers which are not DR or BDR are called two-way. They see each other in hello packets, but do not exchange topology information. These neighbors are then not adjacent, and we can see in the diagram two routers which are operating in two-way state. Looking at some examples using the Cisco iOS configuration syntax, to find an adjacency state, we use the show IP OSPF neighbor command. For OSPF v3, we can do show IPv6 OSPF neighbor. For a point-to-point link, we'll see the state sitting as full. On a broadcast media, we can see routers in a full state, but with either DR or BDR, or in two-way state, as the slide shows.
All right, so adjacencies, a keyword that was missing from my vernacular. Um, let's look at that question again. So this is, yep, correct there. Got that one right. Yeah. So which? Yeah. This is a key. So that doesn't mean that they're not connected to one another. This does not mean that they're not connected to one another. To whatever. It means this. Put it on normal speed.
Shows. Otherwise, neighbor relationships between shows propagate along the adjacencies as the diagram shows. Otherwise, neighbor relationships between routers which are not DR or BDR are called two-way. They see each other in hello packets, but do not exchange topology information. These neighbors are then not adjacent, and we can see in the diagram two routers which are operating in two-way state. Looking at some examples using the Cisco
Okay. So they're not adjacent. They're two-way. All right. Next one. Introduction to OSPF adjacencies. So next one is best configuration practices for OSPF on Cisco iOS. On Cisco iOS, a command like router OSPF XXX enables the routing process. The process ID must be the same as your AS number, the same on across all routers on your network. Different. I think it has to be the same on all. No, it's none of the above, just like before. All right. Which of the following are OSPF best practices? Check all that's apply. Enabling OSPF on links to your peers, upstream providers, and customers. Nope. Setting passive interface default. No. Um, actually, no. This is good. And then you make it unpassive when you want to. So this is good. Letting the router choose a default interface cost. Nope. Configuring interface cost according to your own strategy. Yep. So I think this is right. Yep. Yeah, because then you've got, then you're more intelligently enabling it on the interfaces you want it on, and you don't have to worry about accidentally not configuring, an interface as passive when it needed to be. Which interface does OSPF choose to send out a packet to a given destination address? Uh, so the interface with the lowest OSPF cost, yep. Interface with the sum of all the OSPF costs across the entire. Yeah, this is right because this is the Dijkstra's algorithm, shortest path first algorithm. The interface with the highest available bandwidth, the interface which is carrying the least amount of traffic. Let's check. Yep, got that right. What happens if two paths have the same total end-to-end cost? Um, Load balances. Yep, there we go. So punishment, I got one wrong. Let's watch it.
To start configuring OSPF on Cisco iOS is done the following way. To start OSPF v2, which is for IPv4, we do router OSPF and then a process ID. The process ID can be any number. That number is unique to the router. It's not shared with other neighbors. To start OSPF v3, which is for IPv6 only, we do IPv6 router OSPF and then again the process ID. Some network operators will configure the process ID to be the same as the BGP autonomous system number, but indeed any number will do. To add interfaces in OSPF, we need to look at how we configure OSPF defaults. We start the OSPF process and we mark all interfaces as passive by default. This will prevent OSPF from automatically trying to find a neighbor on every single interface. The ISP best practice is to then activate OSPF on specific interfaces we want to find adjacencies. The last thing we want to do is establish OSPF with external peer or upstream provider, or worse, with one of our customers. Now, in Cisco iOS, enabling OSPF on an interface does two things. First off, it enables the hello protocol to form neighbor relationships and adjacencies with other routers connected to that interface. And it also announces the interface subnets into OSPF. We need to be careful. We really have to avoid enabling hello protocol on untrusted networks, in other words, those outside of your autonomous system. This is industry best practice, but it's a frequent error made by many network operators. And in many cases on public infrastructure, we see network operators leaking the internal OSPF or even trying to find OSPF adjacencies with other infrastructure outside of the network. The I in IGP means interior, and it's really important to remember this in the case of deploying OSPF. Forming neighbor relationships is done by starting the router OSPF process, setting the process ID, marking all interfaces as passive, doing no passive for the interface we want to find adjacency on, and then going to the interface and activating OSPF on it by using the IP OSPF process ID command and specifying which area the interface will sit in. This is the modern configuration syntax. On much older versions of iOS, Cisco used to configure OSPF by running on the subnet. We don't do this anymore. We run OSPF on the actual physical interface. For OSPF version 3, the CLI is exactly the same as the slide shows. This time we're just using IPv6 router OSPF. And to activate on the interface, we do IPv6 OSPF and the process ID, and then specifying which area the interface should be sitting on. Cisco iOS sets the interface cost automatically. Unlike other interior protocols, the cost is calculated based on the interface bandwidth. The formula that iOS uses is 100 million divided by the interface bandwidth in bits per second. So this is fine for interfaces up to 100 megabits per second, which was perfect when OSPF was developed in the early 90s. The fastest interface back then was 50 with 100 megabits per second. But nowadays we see 100 gigabit Ethernet, 400 gigabit Ethernet being developed. This automatic cost generation really does not make any sense. And in fact, many operators today now develop their own interface cost strategy, as they do for interior protocols like ISIS. To do that, it's a simple interface command, IP OSPF cost, and a value which will set the metric on that interface to be this value. Care is needed to make sure that the sum of costs ensures the best path through the network. OSPF chooses the lowest cost path through the network and will load balance over paths with equal cost to the same destination. In this example, we see two paths between the user and the content they are viewing. One path has a cost of 70, the other path has a cost of 60, and OSPF will choose the lowest cost path, 60. Another example, we have equal cost paths. Both of them are 70. So the routers will load balance over the two paths between the content and the end user who is viewing it, even though from the user's perspective, one upstream link is 10 megabits per second and the other upstream link is 2 megabits per second.
All right, so that's best configuration practices. So we're moving right along here. This is so why is it recommended that you enable OSPF neighbor authentication to prevent routes from being injected by unauthorized routers? Yep. Failed authentication prevents the establishment of neighbor relationships and adjacencies with rogue devices. To make OSPF more efficient on a point-to-point link, you could, disable because there's no need for it on point-to-point. So disable the designated router / backup designated router election. OSPF authentication can be enabled on individual interfaces without configuring it on the entire area. True. Yep. Okay, so don't have to watch the video. No punishment for me. Um, okay. Um, all right, comparing OSPF and ISIS. Which of the following statements are true? Check all that apply. ISIS and OSPF, yep, that's true. They're both link state protocols. This is true as well. ISIS and OSPF both use the shortest path first algorithm. Yep, this is true as well. They're both open source protocols. They both originated from Internet Engineering Task Force, not like EIGRP, which was a Cisco proprietary protocol. ISIS and OSPF both support authentication. True. Um, ISIS and OSPF are both carried in user datagrams. That is not true. ISIS is not. OSPF is. Oh, boo. Okay, so no. Whilst IETF extended, extended support To okay, gotcha. It didn't start there. Okay, well, in ISIS, IS stands for Intermediate System. What is an area? What? None of the above. An area. Oh, shoot. Stands for Intermediate System. What is the equivalent concept in OSPF? Um, well, we'll find out. So I got 2 of 4 right. So got to get some punishment here, and then I'll try again.
So in this session, we're going to take a look at two interior routing protocols, ISIS and OSPF. Both of them are linked state routing protocols using the Dijkstra SPF algorithm. So what's the difference between them then? And why do so many ISP engineers spend so much time arguing about which is superior? Well, as we saw in the OSPF session, OSPF stands for Open Shortest Path First. Open means it's an open standard, and developed by the IETF OSPF Working Group in RFC 1247. The current version is OSPF version 2, RFC 2328. The shortest path first refers to Edgar Dijkstra's algorithm for producing a shortest path tree through a graph. ISIS stands for Intermediate System to Intermediate System. ISO 10589 specifies the ISIS routing protocol for CLNS, a link state protocol with a 2-level hierarchical architecture, and it has type length value options to enhance the protocol. RFC 1195 added IP support, and we call this Integrated ISIS. Integrated ISIS runs on top of the data link layer. So let's look at the two protocols. Both are IGPs, Interior Gateway Protocols. They distribute routing information between routers belonging to a single autonomous system, and both use Edgar Dijkstra's algorithm. They support classless interdomain routing, they support variable subnet length masking, they support authentication, they support multipath, and they support unnumbered links. So the slide shows the different terminologies used in OSPF and ISIS for the same devices. In OSPF, we talk about a host. In ISIS, it's an end system. In OSPF, we talk about a router. In ISIS, it's an intermediate system. A link in OSPF is a circuit in ISIS. A packet in OSPF is a protocol data unit in ISIS. Designated router in OSPF is a designated IS in ISIS. OSPF has a backup designated router, and there's no such thing in ISIS. OSPF's link state advertisement is a link state PDU in ISIS. A hello packet in OSPF is the IIH PDU in ISIS. And the database description in OSPF is the complete sequence number PDU in ISIS. OSPF talks about an area, ISIS has a subdomain. OSPF has a non-backbone area, ISIS refers to this as a level 1 or station. OSPF's backbone area is level 2 in ISIS. The area border router in OSPF is an L1, L2 device in ISIS. Autonomous system border router in OSPF is any intermediate system in ISIS. What about the transport? OSPF uses IP as a transport, protocol number 89. ISIS is directly encapsulated in layer 2. It has no dependency on IP.
Okay, yeah, I remember now. Okay, so yeah, they're both link state protocols, both used here. This is not true. They did not both originate from that. They both had development through that, but the development did not originate from that in ISAS. They do both support authentication. Um, so so ISIS stands for an intermediate system. What's a system in OSPF? It's one of the routers. Got it right. All right. Was that all 4? Oh, because this one had 3. Okay, that's why. It's stars, not questions. So there's 2 questions, but you get 4 points. 3 points in the first question, 1 in the next. So these are points, not number of questions. Okay, so configuring. Uh, let's see here. Comparing ISIS and OSPF. Comparing. Ah, there we go. So we only got a few more. I'll probably stop after this. Um, ISIS supports both IPv4 and IPv6 address families in a single routing uh, process. True. With ISIS, you must have the same topology for IPv4 and IPv6. I think that's false. Carrying IPv4 addresses in is possible while supported. False. And this one tripped me up at one point. I thought this was true, but it's definitely false. Alright, I got all these right, so no punishment for me. Moving on. So migrating from OSPF to ISAS is very risky and shouldn't be attempted. Um, I mean, it's true that it's risky, right? I'm gonna go with false. Okay, yeah. Um, the introduction of IPv6 is one of the drivers causing people to look at migrating to ISIS. Very true. All right, so I don't need any punishment, but I'm just curious how it's easy to do it. So let's see if that's in the video.
We're going to use this section to look at how to migrate from OSPF to ISIS. We have been through the process of making a decision about which protocol we should be using, and we may have OSPF already deployed on our network, and we've decided that maybe ISIS is the way we want to go for the future. So how do we do it? It's actually not as difficult as it first might seem. Certainly with the advent of IPv6 and dual-stack networks, more and more network operators are expressing an interest to move over to using ISIS. The presentation is going to describe the process, and it's based on several successful migrations that colleagues have performed over the last decade or so. We'll show you configuration examples using Cisco IOS and Cisco IOS XR. We've covered previously about the motivations. That ISIS runs in the data link layer is perceived to be more secure than using OSPF, which runs on top of IP. We've seen that ISIS is not dependent on IP addressing. And the perception that ISIS has been used for so long by so many of the world's biggest network operators that somehow the equipment vendors would probably be paying more attention to ISIS reliability, scalability, and features than they would do with OSPF. And also the migration to IPv6. Adding IPv6 to our network means OSPF v2 and OSPF v3 are required in the network. Two protocols with two sets of identical configuration to handle IPv4 and IPv6. While there is RFC 5838 to describe support of multiple address families in OSPF v3, there's limited vendor support, and it's not compatible with OSPF version 2 either. For ISIS, we simply add the v6 address family. Most networks today are operating single topology to handle both v4 and v6 prefixes. Newer networks deploying v6 for the first time will often operate ISIS as multi-topology, which allows them to do an incremental deployment of IPv6. Migrate from OSPF to ISIS. We have been through the process of making a decision about which protocol we should be using, and we may have OSPF already deployed on our network, and we've decided that maybe ISIS is the way we want to go for the future. So how do we do it? It's actually not as difficult as it first might seem. Certainly with the advent of IPv6 and dual-stack networks, more and more network operators are expressing an interest to move over to using ISIS. The presentation is going to describe the process, and it's based on several successful migrations that colleagues have performed over the last decade or so. We'll show you configuration examples using Cisco IOS and Cisco IOS XR. We've covered previously about the motivations. That ISIS runs in the data link layer is perceived to be more secure than using OSPF, which runs on top of IP. We've seen that ISIS is not dependent on IP addressing. And the perception that ISIS has been used for so long by so many of the world's biggest network operators that somehow the equipment vendors would probably be paying more attention to ISIS reliability, scalability, and features than they would do with OSPF. And also the migration to IPv6. Adding
Okay, so they're going to show the migration plan next, it looks like. And that will explain why it's easy. Yeah. All right, so why is it safe to start deploying ISIS on a live OSPF network? Um, oh, I think it's this. The default administrative distance for OSPF is lower than ISIS, so OSPF routes are preferred. Got it right. That's right. If you learn the same prefix through both OSPF and ISIS, the route with the lowest administrative distance is the one chosen to go into the global RIB. So you could just slap ISIS on there, and it doesn't do anything because it'll just keep using the OSPF. And then once you've got it all set up and working, you just delete the OSPF, and then it uses the ISIS. That's brilliant. Exercises. Put the steps in the plan for migrating from OSPF to ICS in order. All right, well, let's think about it. So this is definitely going to be the last thing you would do. Um, so, um, so the first thing you would do would be just to verify the operation. Um, then, okay, so this would be the second to last thing. The last thing you would do is check for any remaining. Um, uh, then you'd want to make sure that you set it higher and then like that. Oh, I got it all wrong. Interesting. Okay, well I gotta watch the video. Well, let's see if I can figure it out. So this one was right. Verify that. Um, I think next you would deploy ISIS. Okay, then you would deploy. Then you would. Okay, so yeah, you can keep the administrative distance. You can keep it on, and then yeah. Okay, gotcha. Check for any. Yeah, okay. So you can basically delete it without deleting it first by adjusting the administrative distance. Yeah, so this is right. So that's what you should do before you remove it off. You should then change the administrative distance of OSPF to be higher than ISIS. So now ISIS is preferred. A dinner. Oh, right. Yeah, I was working with the AI, and I'm gonna eat dinner at 5. Okay, gotcha. There's not like a dinner that I'm traveling to or anything. All right, so perfect. So yeah, this makes sense. So before you delete it, you can basically soft delete it before you hard delete it by changing the administrative distance. So nope. So yeah, we got a punishment video to watch here.
Before we start, we need to come up with a migration plan. The migration plan is very simple. We'll look at it in the next few slides. First off, we verify the OSPF configuration in operation. We need to check that what we've got is actually working. We deploy ISIs over the entire backbone. We change the administrative distance of OSPF to be higher than that of ISIs, and that's the key. We check for remnants in OSPF, and then we remove OSPF for the entire backbone, and finally confirm ISI's operation. So let's look at each in turn. First off, verifying the OSPF configuration. So this is implementing all the good practices that we have discussed elsewhere in the series. For example, next hop south for IBGP, so that we do not carry external point-to-point links in OSPF. If we do need to carry external point-to-point links, for example, for monitoring, we carry them in IBGP and tag them with a specific community which is visible to the monitoring system only. We remove surplus OSPF network statements. Older versions of Cisco IOS could only handle network statement configuration. In other words, OSPF ran on the subnet, not on the link. For more modern versions of Cisco IOS, those from 12.4 onwards, and Cisco IOS XR, OSPF is operated on the physical interface instead. So we want to modernize our configuration so that it all performs like this. The slide shows a configuration example if you're still running an iOS prior to 12.4. I would recommend running such an old piece of software, but realistically, some networks still have to do this. If you are, then this is the type of configuration required, as an example. More modern versions of the iOS have the example shown in the slide, where OSPF has been configured on each interface. And this slide shows how the same thing may be configured using Cisco IOS XR, where again OSPF is activated on each interface that requires the adjacency. If IPv6 has already been deployed, then we need to tidy up the OSPF version 3 configuration in the same way as we tidied up OSPF version 2. In Cisco IOS, the router OSPF configuration should look identical to the IPv6 router OSPF configuration. For iOS XR, the router OSPF configuration should look identical to the router OSPF v3 configuration. It's essential for the network operator to compare the two configurations for OSPF v2 and OSPF v3 and make sure they are identical. And also check that the IPv4 adjacencies match the IPv6 adjacencies. We don't want to miss anything out. Once we have done the configuration check on the network, we should verify OSPF's operation. Verifying operation is important after any cleanup. We need to make sure that the IBGP peers are stable, that the next hop values are all valid, and that the OSPF routing table is complete. If we've already deployed IPv6, we need to check that OSPF v3 configuration is working the same as the OSPF v2 configuration. So as well as all the adjacencies, we want to compare routing table entries and so forth. Once we've done this, we're now in a position to deploy ISIs over the entire backbone. ISPs will deploy IPv6 dual stack across their infrastructure. Every device running an IPv4 IGP will also require to run an IPv6 IGP. They may choose single topology ISIs, where the v4 and v6 topology is identical across the whole backbone. This needs care though, as adjacent routers need to have both IPv4 and IPv6 on the link. These days, more operators are choosing to use multi-topology ISIs, where the v4 and v6 topology can differ. And this gives a lot more flexibility for operators who are doing incremental rollouts of IPv6. The ISI's deployment can happen at any time, because, at least on Cisco IOS and most other vendors, the ISI's protocol distance is higher than that of OSPF's. A higher protocol distance means the protocol has lower priority. So even if ISIs is up and running and carrying adjacencies and reachability information, OSPF will still take priority. We need to use wide metrics, which is required for v6 address family support in any case. And note that we only want to use level 2 IS. Cisco IOS default is L1, L2. As for v6 addressing, the network operator has a choice of using global unicast addresses or link local addressing with unnumbered interfaces. The slide shows a configuration example using Cisco IOS. We have a loopback interface with v4 and v6 address on it, and we have an Ethernet interface using a v4 global address and a v6 unnumbered address based on the loopback. We've configured ISIs in the v4 address family, and we've configured ISIs in the v6 address family on that interface, and set metrics for both v4 and v6. The following slide, which is the second part of the configuration, shows another example interface and then how the ISI's process itself is configured. Note the key features. The NET address, the passive interface for the loopback, we've set the IS type to be level 2 only, we've set wide metrics, and we've configured the overload bit so that ISIs will not announce it being best path until BGP is operational. For the v6 address family, we have created multi-topology, so we're running a separate topology, and we've also set the overload bit for the v6 configuration. I have a similar configuration on the screen now for iOS XR, the same interfaces, and then the same ISI's configuration. Notice that iOS XR, the ISI's configuration for each interface is configured within the ISI's process itself. Other vendors use this style of configuration syntax also.
All right. So final one, and then I think I'll be done for a while. So migration from OSPF to ISIS. How do you make each router prefer ISIS routes over OSPF routes to insert into the global RIB? You change the administrative distance, the lower one the better. Directly connected have 0, so you can't get any better than that. But OSPF by default has lower than ISIS, so you can raise the distance and prefer ISIS. There should be no OSPF routes visible in the global RIB before you turn off OSPF. True, you should do a soft turn off before a hard turn off. There you go. So there we go. And so next one is the introduction to BGP. Yep, so click on the this, yep, we've got cool. The links change. So yeah, that's gonna be it for this video. This is cool. I like this a lot. This is the best learning resource I've encountered for network engineering in a long time. So I think I'm gonna make this kind of the mainstay of this channel for a while. So I hope people like it. Thanks for watching, and see you in the next one.